And welcome back. As we continue our cosmic journey, let's go ahead and talk about observations that are done outside of Earth's atmosphere. So, Earth's atmosphere has a couple drawbacks when it comes to trying to do observations. First of all, it blocks most radiation at wavelengths shorter than visible light, so we can only make direct ultraviolet, X-ray, and gamma ray observations from space. Getting above the distorting effects of the atmosphere is also an advantage at visible and infrared wavelengths, because when you're up in space, you have things like the stars aren't twinkling due to atmospheric distortion, so the amount of detail that we can observe is limited only therefore by the size of the instrument. On the other hand, it is very expensive to place telescopes in space, and repairs can present a major challenge. For example, the Hubble was a whole operation for it to replace the flaws that it had when it was operating. This is why astronomers continue to build telescopes that are on the ground, as well as also looking at ones that they can launch into space. So let's talk about some of the airborne and space infrared telescopes. Water vapor, which is the main source of atmospheric interference for making infrared observation, is concentrated in the lower part of Earth's atmosphere. For this reason, a gain of even a few hundred meters in elevation, so not that far comparatively, can make an important difference in the quality of an infrared observatory. Now, given the limitations of high mountains, most of which attract clouds and violent storms, and the fact that the ability of humans to perform complex tasks degrades at high altitudes because of things like lack of oxygen, it was natural for astronomers to investigate the possibility of observing infrared waves either from airplanes or ultimately looking at doing it from space. Now, infrared observations from airplanes have been made since the 1960s, starting with the 15-centimeter telescope on board a Learjet. So let's talk a little bit about infrared astronomy itself. One of the important things here is that getting higher and higher into the atmosphere and make your way into space allows to have some important advantages that infrared astronomy may not otherwise benefit from when you are lower. First, of course, is the elimination of the interference from the atmosphere. We already talked about how water vapor is one of those things that presents a key challenge because it absorbs a lot of that infrared. Equally important is the opportunity to cool the entire optical system of the instrument to nearly eliminate infrared radiation from the telescope itself, because the telescope is also going to have some residual heat, and so that could affect the sensors and stuff like that you're trying to use to actually capture some of this information. Now, if we try to cool a telescope with the atmosphere, one of the disadvantages is that it would quickly become coated with condensing water vapor and other gases, kind of making it useless. So any of those tools that we're trying to use, because hey, we got to cool this down, guess what it's going to do? All those gases are going to condense, start forming liquids, and we don't want that to happen. So only in the vacuum of space can optical instruments be cooled to hundreds of degrees below freezing and remain operational, because again, in the vacuum of space, we don't have this giant collection of gases and water vapor that's going to try to condense. Now, with those observatories that we put in space, obviously we're looking at them being in orbit. The first orbiting infrared observatory was launched in 1983. It was known as the Infrared Astronomical Satellite, or IRAS, built as a joint project by the United States, the Netherlands, and Britain. For the first time, the infrared sky could be seen as if it were night, rather than through a bright foreground of atmospheric and telescope emissions. Now, IRAS carried out a rapid but comprehensive survey of the entire infrared sky over a 10-month period, cataloging about 350,000 sources of infrared radiation. Now, of course, since then, we have several other infrared telescopes that have operated in space with much better sensitivity and resolution due to improvements in infrared detectors. Now, the most powerful of these early infrared telescopes was the 0.5-meter Spitzer Space Telescope, which was launched in 2003 and ended operations in 2020. However, now we have a much more powerful telescope which can do that, which of course is the James Webb Telescope. Now, we're going to continue to build larger and more sensitive infrared telescopes in space because they help us detect the cooler parts of cosmic objects, such as the dust clouds around nurseries of infant stars, and even the remnants of dying stars that visible light images cannot reveal, because there's a lot of information that is present there that you can't find in visible light. So one of our special telescope friends is the Hubble Space Telescope, which I already talked about. Now, Hubble is very, very important for astronomy because astronomers have obtained some of the most detailed images of the astronomical objects from the solar system outward all the way to the most distant galaxies. Among its many achievements is the Hubble Ultra Deep Field. It's an image of a small region of the sky that was observed for almost 100 hours. Now, this deep view contains views of about, let's say, 10,000 galaxies, some of which, if you were to actually do the math on, you'd find that they formed when the universe was just 1% of its current age. Now, the other telescope we mentioned was the James Webb Space Telescope. This is one of the largest telescopes that we've sent into space so far, and it is one that's specifically designed to observe infrared radiation from the universe. It was launched on December 25th, 2021, and the telescope is now in a stable orbit about 1.5 million kilometers from Earth, or 4 times further from the Moon. This location is actually really good for infrared because it's a nice cold location, but there is a slight disadvantage. Because it is so far out, it is in a place where no astronauts can currently travel if it were in need of repair. Now, one of the reasons why Webb is so good is it has an 18-segment primary mirror that is 6.5 meters in diameter. There's also a multi-layer shield the size of a tennis court that helps protect it from the heat of the sun and allows its liquid helium-cooled instruments to gather extremely faint infrared radiation from the universe. Now, NASA estimates that the resolution of this telescope would be sufficient to distinguish a U.S. penny that was held up 40 kilometers away. So if you were holding a penny in your hand and you were 40 kilometers away, you could see that. So let's just look at a few of those images that James Webb Telescope can do and what that's going to produce. So the first is the Southern Ring Nebula, and here we are looking at material that's been expelled from a dying star. Now, you'll notice that on visible light images, if you were to look at the same nebula, only one star can be seen here, but in the infrared spectrum, which we are looking at right now, we can see there are 2 stars in the nebula's central region. And of these 2 stars here, they're right here in the middle, it is the dying reddish star, which is over here to the left, that is responsible for the shells of dusty material that are around the nebula. But this companion star, the one that's on the right, makes that dying star kind of wobble a little bit, explaining some of the spiky asymmetrical structure that you see here in the nebula. Now, the other image we have here is 7th Quintet. Now, about 1,000 different image files were combined into this detailed portrait of a compact group of galaxies. Now, what's interesting is that only 4 of these galaxies actually move together in space. The 5th galaxy, which is this one here on the left, is actually much closer to us than the other 4, and it just happens to kind of line up with the other 4 galaxies here in this image. Now, one thing you will notice that we kind of have some of these sweeping tails that are coming off of these galaxies, and that's because these 4 galaxies, because they are so close, are actually being pulled out from one another. So you're pulling material off from one another from these galaxies by the proximity of their neighbors. Now, space telescopes are pretty cool, but what are other things that they can do? Well, we can have some high-energy observatories work for us. Ultraviolet, X-ray, and direct gamma ray observations can only be made from space. Among recent X-ray telescopes is the Chandra X-ray Observatory, which was launched in 1999. It is producing X-ray images with unprecedented resolution and sensitivity. Now, designing instruments that can collect and focus energetic radiation, such as X-rays and gamma rays, is an enormous technological challenge. So, in 2008, NASA launched the Fermi Gamma Ray Space Telescope, which was designed to measure cosmic gamma rays at energies greater than any previous telescope, and thus able to collect radiation from some of the most energetic events in the universe. So, with X-rays and gamma rays, one of the major challenges with it is to design mirrors that can reflect such penetrating radiation which would normally pass straight through it. So the 3 basic components of an observing system are the same no matter what wavelength. You have a telescope that's going to gather up some radiation, you have filters or instruments to sort that radiation according to the wavelength, and they're going to have some method of detecting and making a permanent record of that observation. Now, gamma ray detections can also be made from Earth's surface using the atmosphere as the primary detector. When a gamma ray hits our atmosphere, it accelerates charged particles, mostly electrons, in the atmosphere. Now, those energetic particles hit other particles in the atmosphere and give off their own radiation. Now, this effect is a cascade of light and energy that can be detected on the ground. In fact, the Veritas array in Arizona and the HESS array in Namibia